Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we have two things in our platter. Okay, first thing will be SHM and the second will be a measurement and error analysis. First 3 days we will be looking into SHM and the final 2 days we will talk about measurement and error analysis. So in this class, okay, let's talk about the kinematics of SHM. So without losing any further time, let me share my screen with you people. So here we go. So as we know that about SHM, that when a system is displaced slightly from its stable equilibrium position and released, a restoring force tries to bring it back to original position. But as the particle reaches its original equilibrium position, it gains some speed due to which it moves to other extreme and so on. Okay, so it will keep on oscillating about mean position. A pattern of motion will be repeated at regular time interval, and this kind of motion is known as oscillatory motion. SHM is a special case of oscillatory motion. So let's try to figure this thing using a potential energy curve. So let's say we have some potential energy U versus X curve in which we are able to locate some stable equilibrium position. So you can see that this position here, right here, is a stable equilibrium position. Okay, that means when the system will be here, it will be experiencing zero net force. Okay, and also if I displace it slightly from here to here, let's say, okay, it will start experiencing a restoring force, because at this position you can see that df by dx is nothing but negative quantity. Alternatively, you could clearly see that d2u by dx square is a positive quantity and f is nothing but minus du by dx. So here df by dx is a negative quantity, so that is why a restoring force will try to bring it to its original equilibrium position. But what we have done exactly over here, so at when we have brought at this position, okay, we have provided it with some potential energy. So u is, let's say, u naught over here, so like, or delta u is u naught over here. So when it will get back to its stable equilibrium position, all this potential energy will get converted into kinetic energy. So when it will come over here, it will be having some kinetic energy. So due to that kinetic energy, it will be moving to the other extremes, and again the kinetic energy will turn out to be equal to zero, but again a restoring force will try to bring it back, and henceforth and so on. Okay, so this motion will continue if there is no leakage of energy from the system. Potential energy will keep converting into kinetic energy, and kinetic energy will keep converting into potential energy, and this oscillation will keep on going about this stable equilibrium position, which would be known as mean position in this case. Okay, so like that is the analysis. And let's look at one special case which we are saying it as SHM. So that is a special case of oscillatory motion when we will be having this df by dx is equal to let's say some constant, and that would be some minus k over. Obviously it is a negative, so k here we have taken it as a positive quantity over. Df by dx is a constant. Okay, so see, df we can write it as minus k dx over here, and when we will integrate it with appropriate limits, so let's choose our references appropriately so that this equation looks good. So let's say initial potential energy, let's say this is stable equilibrium position, we have assigned it x is equal to 0 coordinate, and at this position we have assigned the potential energy to be equal to 0 at this position. Okay, so let's put the limit. So at x is equal to 0, okay, the force would be 0 as well, because here no force is acting. And here, as a function of x, we want this force Okay, so solving this, we will be simply getting f is equal to minus kx over here. Always understand this x is not position, but it is displacement from the mean position. Position will be equal to displacement from mean position if we have chosen the stable equilibrium position or the mean position to be origin itself. So f is equal to minus kx, and this represents basically simple harmonic motion. So this, when you will represent it in differential equation form, so f is equal to nothing but mass times acceleration, that is m times d2x by dt square is equal to minus kx, or simply you can write it as plus kx, and that will be equal to 0. You must understand the solution to this. The general solution to this is nothing but x is equal to a sine or cos, whatever you want to wish to write. So a sine omega t plus phi over here. Okay, where you should also realize where omega is known as the angular frequency of SHM, and that will turn out to be root under k by m, where k is this constant over here and m is the mass of the system. So this is how we get a equation of SHM when the restoring force over here is a constant, that is minus k. And now let's look into the kinematics of this situation. Okay, so let's talk about kinematics of SHM. So as we have already understood that the position versus time function as represented by x is equal to a sine omega t plus less some phi naught over here. This whole thing omega t plus phi naught is known as phase of SHM, which you see is a function of time. It varies with respect to time. So when the phase of SHM varies with respect to time, similarly it will vary the position as function of time. So x is represented as a sine omega t plus phi naught, where omega is angular frequency, as we have already stated. Here a is termed as the amplitude of SHM, which is nothing but maximum displacement from the mean position. Okay, and this phi naught, see, this omega t plus phi naught is the phase, and this phi naught is termed as initial phase, because at t is equal to 0, the phase of SHM will be nothing but phi naught over here. So that is how SHM is represented as function of time. Position will be represented as function of time this way. Okay, and here let me introduce one simple concept. Like, see, you can see the position is varying with respect to time, and this is not a uniform variation, means velocity of this particle along x-axis is not uniform. So let me introduce a concept of reference circle. Okay, reference circle. So let's imagine, let's say this is x-axis and this is y-axis, and this is origin over here. So let's imagine a circular path, or a circle, simply say, of radius a, which is centered at origin. And let's imagine some particle initially is here. Okay, and this angle here is nothing but, let's say, phi naught. Okay, and this particle is moving uniformly on this circular path with a uniform angular velocity, say omega. So in time t, after time t, where it will reach? So it will reach somewhere over here. Let's say this angle it will cover, angular displacement would be nothing but omega t. So the particle will reach over here. So where will its projection lie on the x-axis? So this would be somewhere here. So this is nothing but the projection of this particle which is moving on the reference circle on x-axis. So what would that quantity be? So you can clearly understand that this x is nothing but, since this whole angle is nothing but omega t plus phi naught, so x you can write it as a sine omega t plus phi naught, where a will be the radius of the circular path over here, or reference circle you can say. So looking at this expression, simply you can say that as the particle moves on reference circle with constant angular speed omega, its projection on x-axis execute SHM about origin with angular frequency omega with an amplitude a, obviously. So what would be its time period? Time period of the oscillation, obviously this pattern will be repeating itself at a regular time interval. So in the same time this will take for this particle to complete one revolution. Okay, its projection will take the same time to complete one oscillation. So time period obviously would be nothing but 2 pi upon omega over here, and delta t is equal to nothing but, let's say, some delta theta would be the angular displacement. So delta theta upon omega, you can say. Why I am introducing this concept of reference circle? Because see, the motion of this particle along x-axis is non-uniform. Okay, so if you wish to find out like how much time will it take for this particle to move from this position to that position, since the motion is non-uniform, you will not be able to write like delta t is equal to delta x upon v kind of thing. This would be completely wrong because v is not constant, the motion is non-uniform. Rather, one simple way of dealing with this situation, that you can see the motion of the particle on the reference circle, okay, is uniform. Okay, so in order to find out how much time will it take to move from one angular position to another angular position, the time period, the time interval we will be able to find out will be quite easy. Okay, so whenever we are required to find out how much time it will take for the particle to move from one position to another position, we must imagine that what are the corresponding positions of the particle on the reference circle and how much time will it take to move from one angular position to another position, and we must use this formula. Let's take one very simple question regarding this, and let me give you the question over here. So let's say this is the question. Okay, so here the question is: a particle executing SHM along x-axis about origin with angular frequency omega and amplitude a is initially at x is equal to a by 2 and moving away from the origin. So on x-axis, when you will see, on x-axis this is say origin, and this would be one of the extreme, this would be the another extreme. So this is x is equal to plus a, this is equal to x is equal to minus a. So you can see the initially the particle is here, initially the particle is somewhere at x is equal to a by 2, and it is moving away from origin, means it is moving in this direction, and we wish to find out like how much minimum time it will take to move from this position to this position. This position is given to us as x is equal to minus a by root 2. So what we must do? So the idea here is, let's say we must be drawing the reference circle over here. So this would be somewhere kind of reference circle. Pardon for my bad mm, uh, diagram over here. Let me draw it again. So this would be something like this. This is the reference circle. Okay, so initially the corresponding position on the reference circle could be either this or that. Okay, and since this is moving along this direction and we have taken the angular velocity direction to be this, so obviously this would be, the particle would be here on the reference circle, and when it would be moving in this direction, its projection would be moving away from origin. So initially it is here. Okay, so when it is moving away from origin, you should realize on this circular path it will move like this, and it has to reach, it has to reach either this position or that position. So first you must realize it would be reaching over here. Let me use another color pen. So like this would be the path of the particle on the reference circle, you should realize. Okay, so this is the idea over here. So basically we must try to find out the angular displacement over here. So this angle you should realize is nothing but, first of all, since this is equal to x is equal to a by 2, so this angle would be pi by 6. And you should also realize this is x is equal to minus a by root 2. So this angle is nothing but pi by 4 over here. So it is clear that when the particle move on the x-axis from this position to this position, okay, the uh, particle on the reference circle will move from this position to this position. So this would here would be the angular displacement, say delta theta. And delta theta, you should realize, is nothing but uh, this angle here is basically pi by 3, and this here is pi by 2, and this here is pi by 4. So pi by 3 plus pi by 2 plus pi by 4 over here, obviously you will be able to add that. So once delta theta you know, okay, so delta t you will be able to find out. That would be nothing but delta theta upon omega over here, and omega is given in the question. So that would be the answer for the first part. And the answer for the second part over here is simple. Like when they are asking the average velocity, so average velocity you can say is nothing but displacement upon time interval. So displacement, you should realize, this is the initial position and this is the final position. So this would be the displacement. Okay, displacement, as you understand, depends upon final and initial position only. So this here would be displacement, and that would be nothing but displacement you can say is negative. So that would be nothing but this gap is a by 2, this gap is a by root 2. So that would be minus a into 1 by 2 plus 1 by root 2, and that divided by delta t, which we have already found out. So when we are trying to find out the average speed, now you realize, in order to find out the average speed, we have to find out the total distance traveled upon total time over here. So distance traveled, since this particle is moving from this to this, from to this extreme here, and then it will be going back over here. So the length of this path here would be nothing but the distance traveled, and distance traveled from here to here, you can see a, you can take common, and that would be 1 by 2. And from here to here again a, so plus 1, and from here to here again 1 by root 2. So this is the distance traveled and upon the time interval, which we have already found out. So this is how you can solve this question. Let's take one another simple example. Okay, this. So say two particle executing SHM with same amplitude A and same frequency along same straight line, they cross each other moving in opposite direction. Each time their displacement is A by root 2 from the mean position. And we have to find out the phase difference between them. So again, we will be using the reference circle in order to solve this question. So their positions are x is equal to a by root 2. That is the displacement from the mean position. So you should realize we are talking about something like this line. This is x is equal to a by root 2, say. So they cross each other moving in opposite direction. So one particle is definitely moving in this direction and the another particle is moving in this direction. Okay, so you must realize, if omega is in this direction, the particle which is moving away from the origin might be right here, and the particle which is moving towards the origin, that might be right here. Okay, so these are the two particles which are moving on the reference circle, and their projections are moving on the x-axis over here, as you can see. So if we are required to find out the phase difference, simply we are looking to find out basically this angle we wish to find out. And finding out this angle is geometrically very simple, since x is equal to a by root 2. This is a by root 2, this is a. So this angle definitely is pi by 4. So this angle is definitely pi by 4 as well. And delta phi, you can say, is nothing but simply pi by 2. So that is a very simple question. Okay, so now let's move on to the another concept, and let's look at two special cases when we are dealing with SHM. these two special cases arise very frequently. One special case is like the particle motion when we are describing the SHM, and the particle's initial position is given as that is starting from mean position. Okay, either they give starting from mean position, that is one of the special case, and the another is starting from, sorry, uh, extreme position. Okay, and that is, I think my pen is not working properly. So that is starting from extreme position, So whenever we are having a case when it is starting from mean position, okay, you should realize that x is equal to 0 at t is equal to 0, and you should realize we can represent it as x is equal to a sine omega t. Okay, so let me figure out what has happened here. I'm not able to write properly. So x is equal to a sine omega t we can write, and here starting from extreme position, so you should realize like at t is equal to 0, at t is equal to 0, we are having x is equal to say plus a. Okay, so we will be representing it as x is equal to a cos omega t, right? I don't know what has happened. Okay, now I'm able to write properly. So this is x is equal to a cos omega t. So you should realize, so depending upon the starting position, okay, whether we are starting from the mean position or starting from the extreme position, we can have the different equation to start with. That is either x is equal to a sine omega t or x is equal to a cos omega t. But you should realize that both expression represents the same SHM. That is motion of particle executing SHM about x is equal to 0 with amplitude a and angular frequency omega, and that is all that matters. Okay, only the initial phases differ, okay, which is due to because the observation of motion has been started at different instances, and there is no other difference in these two relationship apart from that, except that the observation has been started at different moment. Both these expressions represent the same motion, same SHM, okay, because they are having same amplitude, same angular frequency also, and same mean position as well. Okay, so it does not matter whether you represent it like this or represent it like this difference is only arising due to the starting position. Okay, so let's take one simple question where we will be using that. Okay, so let's have this question here. So this is the question. A particle execute SHM in a straight line starting from rest, and it travels a distance a in the first second and distance b in the next second in same direction, and we have to prove that this one would be the amplitude. Okay, so you should realize in the given question it is given starting from rest. Starting from rest means initially the particle is at its extreme position. So you should represent the equation of SHM something like x is equal to a cos omega t, because the particle is initially at extreme position. And now we can uh, put in the information that is given in the question. So let's say this is the x-axis and this is the origin and this is the say amplitude. So this is x is equal to a and this would be x is equal to minus a. Okay, so initially the particle is somewhere here. So in the first second, in 1 second you can say the particle has reached from here to here. It has traveled by a distance a. Okay, so obviously this position is nothing but x is equal to capital A minus A. And in the next 1 second, and again next 1 second, it has traveled by a distance b. So this position over here is nothing but x is equal to A minus this total distance, that is A minus A plus B, that you should realize. Okay, so that has been given to us. Obviously, you should realize in the first second it will travel to a lesser distance, and in the next second it would be moving faster and will be traveling greater distance. So like this, A and B definitely are not equal. So we have to find out now the amplitude of this thing over here. So two equations we can write. So for in 1 second, which we have realized, just substituting the value of time t and x. So the first equation we will be getting is A minus A would be nothing but capital A into cos omega, and t is basically 1. So cos omega simply we can write. So that is first equation. And the second equation would be capital A minus A plus B into A cos 2 omega we can write. So that is equation number 2. Okay, so cos 2 omega definitely can be represented as, let me solve a little bit. I will not solve it completely. Okay, I will just do a few steps and leave it to you then. So that is, for example, A, and cos 2 omega, you should realize, is nothing but 2 cos square omega minus 1. So 2 and cos square omega, you should realize here this is cos omega. So cos omega is nothing but 1 minus A by A, you should realize, and 2 cos square omega minus 1. Okay, so so this equation here is solving this, it will directly give you A, because anyway we have eliminated this omega. Okay, so A you will be getting by solving this equation. That will be very, very easy. So that would be 2A square upon 3A minus B. Okay, so that is how you can do that. Like the thing I wanted you to notice was this thing, that whenever we are having something like starting from rest, we must use this equation. Okay, another variation of this problem of kinematics of SHM, sometimes origin is not at mean position. What we had been taking, like wherever the mean position was, we had assigned the coordinates x is equal to 0 to that mean position. But what if this is not the case? Okay, so let's take a case of like when origin is not at mean position. Okay, so how will the equation look like? Let's say, for example, this is the origin. Okay, and this is some x is equal to x naught, and let's say amplitude is a. So it will move the displacement, maximum displacement from mean position, that would be a. So this extreme position will be having coordinates x is equal to x naught plus a, and the another extreme would be having coordinate. So since this is a, this would be x is equal to x naught minus a. Okay, so here x as function of time, you can simply represent it as x is equal to x naught plus a cos omega t. And when you will be closely looking at it, this is nothing but x minus x naught is equal to a cos omega t. And let's represent this quantity as some capital X. So x is equal to a cos omega t. So you can see the form is still same, only the, like, see the what we have been saying from the very beginning, that this x is not position, rather it is displacement from the mean position. And displacement from the mean position, when the mean position is x naught, will be represented something like this. Okay, so that is the idea. Okay, so let's have a very simple question regarding this. So this is the question. So you can see that a particle is executing SHM along x-axis about mean position. This time I have taken some other mean position. X is equal to 5 with angular frequency pi radian per second and amplitude 6 meter. Initially it is at x is equal to 2 and moving towards origin. And what minimum time will it take to reach x is equal to 5 position? So that you can see that this question is the old problems which we already solved, only the difference is the mean position is no longer origin. So how we are going to approach this problem? Okay, so say this is second. So this is, let's say, x-axis. Okay, and here this is our mean position, let's say, that is x is equal to 5. Again my pen is not working properly. So let me do a few stuffs over here. Okay, so x is equal to a cos omega t is given. So the question which we were solving was this. So the mean position is nothing but x is equal to 5. X is equal to 5. Okay, and initially it is at x is equal to 2. So where would be the other extreme positions? The amplitude is nothing but 6 meter. So what we can draw is a reference circle of radius 6 meter. So this radius here is basically 6 meters. So this would be nothing but x is equal to 11, and this would be nothing but x is equal to -1 over here. And initially it has been given to us that the particle is at x is equal to 2. So somewhere here that would be x is equal to 2. So basically its initial displacement from the mean position is nothing but 3 meter over here. Okay, so its position on the reference circle is this. Okay, so this angle is nothing but you should realize that is pi by 6. Okay, and initially it is moving towards the origin. Origin would be somewhere here. So it is moving in this direction. Okay, so it's you should realize if I take the clockwise direction as positive, so if it is moving towards the origin, so like basically rather you must say that this is its position. Rather being this as position, because it is moving toward origin, you must say that it is here. Okay, because we generally take the clockwise sense of the rotation. Okay, and it has to reach the origin. So the uh, nearest position, angular position, would be this over here. So basically this angular displacement we want to cover. Okay, so this angle is nothing but pi by 6 over here. So delta theta, you should realize, is nothing but pi by 2. Okay, this angle is pi by 2, and this angle here, uh, this is pi by 2, and this angle here would be you can say pi by 3. So pi by 2 plus pi by 3 would be 5 pi by 6, you can say. So that would be delta theta, and delta t, obviously you will be able to find it as delta phi or delta theta upon omega over here. Okay, so this is the idea. And I'm not able to write properly today because see, like, I don't know what has happened to the pen. So anyway, let's continue whatever we can do today. Okay, so this was one of the case when origin is not at the mean position, right? And now let's look at another thing, that is velocity and acceleration. So velocity and acceleration also. Let's try to look at these parameters. So as we have already represented, x is equal to a sine omega t. Okay, and if we wish to find out the velocity, v would be nothing but dx by dt, which would give us a omega cos omega t. Okay, and acceleration, very simply we can find out, okay, that is dv by dt, that would be nothing but minus omega square a sine omega t. And also you should realize, like this a omega, if we represent it as v naught cos omega t, okay, observing that v naught is nothing but a omega, which is the maximum velocity or maximum speed during the motion, and this can be represented as minus a naught into sine omega t. And here we can see that a naught is nothing but omega square a. So here we were able to represent v and a as function of time. Okay, so all are varying sinusoidally with same time period over here because they have same angular frequency. So if we plot their graphs, okay, time graphs over here, so let's say this is the time axis, so you should realize the displacement will be varying, okay, between the extreme plus a and minus a. And since I have represented it as sine, so it would be something like this. Okay, you should realize this is 0, and this time would be nothing but pi by 2 omega. This time would be nothing but pi by omega. This is nothing but you can say 3 pi by 2 omega, and this here is nothing but 2 pi by omega over here. Okay, so this pattern will keep on repeating itself, you should realize. Okay, so if this is a, okay, so you should also we should also try to figure out what would be the amplitude, what would be the acceleration over here. So acceleration is nothing but minus omega square a sine omega t. So its amplitude would be varying between, like its amplitude is omega square a, so acceleration would be varying between uh, a naught, which is omega square a, and minus a naught over here. So its graph will look something like this. Okay, and if we wish to plot the velocity, so velocity's expression is v naught cos omega t. So its amplitude of oscillation is nothing but it will be oscillating between say plus v naught to minus v naught over here. Okay, and it is represented by cos function, so its graph will look something like this. Okay, so you can see, like here all these functions of time, for example x, v and a, are sinusoidal functions of time. That means they are varying with a time period of 2 pi by omega, all of them, but they are having a phase difference, and you should realize this fact, okay, that v is leading x, v leads x by a phase of pi by 2, and similarly you can say a leads v by a phase of pi by 2. You can say, like when we differentiate a sinusoidal function with respect to time, the function which we get after differentiating leads the previous function, okay, by a phase of pi by 2. So that you can see also in this diagram that the blue curve is leading the black curve by a phase of pi by 2. This simply means that whenever we will be having the particle at mean position, the speed would be maximum, and when the speed would be 0, the particle would be at either of the extreme position. So that is what it means when we say that there is a phase difference of pi by 2 between v and x or a and v, etc. So that is the idea. So here we have represented uh, x, v, and a as function of time. So let's try to introduce uh, them as function of v as function of x and a as function of x as well. Okay, so you can see that x, I had represented it as a sine omega t, and v, I had represented it as a omega cos omega t. So from these two equations, when you will be eliminating omega t, for example, sine omega t is nothing but x by a, and cos omega t is nothing but v upon a omega. So squaring and adding will simply give you x square upon a square plus v square upon a square omega square is equal to 1. Okay, and rearranging this expression will also give you that v is equal to plus minus omega root under a square minus x square over here. So this is a relationship between v and x, which enables you to find out the velocity as function of x. When you will be plotting this graph you can plot. Okay, so that you can see that is the equation of an ellipse. So let's say this axis is x and this axis is the velocity axis. So it will be looking like this, like an ellipse. Okay, this extreme obviously is x is equal to plus a and x is equal to minus a, and this is nothing but v is equal to a omega, and this is v is equal to minus a omega. The important thing to notice in this, okay, like for example, for a given position, like let's say about this position x is equal to x naught, okay, we are having two possible velocities, okay, two possible velocities, okay, but you should realize that the speeds are same. Okay, the magnitude of these velocities are same, but we are having two possible velocities. So that means, like, whenever a particle is executing SHM, and let's say this particle is here, so at this instant it can have velocity either in this direction or in this direction, but they will be having same speeds at these two different instances, you should realize. So for a given x we will be having two possible velocities, and also you should realize for a given v we can have two possible positions also. Okay, let's say for example this is the given v, and we are having two possible, this position it will be having velocity v, let's say it is moving in this direction, and at this position also it will be having the velocity v. So there are two possible position in which we will be having the same velocity. Okay, so let's take one simple question regarding this. Okay, so this is the question over here, that is a particle execute SHM along x-axis about origin. Okay, and when it is at x is equal to x1, okay, uh, and x is equal to x2, its speeds are v1 and v2 respectively, and we have to find out the time periods over here. So you should realize like how x and v are related to each other. So when you will be substituting these in the given equation which we have already learned, v is equal to, since we have learned that plus minus omega root under a square minus x square, so then let's substitute these values. So first equation we will be getting is v1 square is equal to omega square into a square minus x1 square, and the another equation we will be getting is v2 square is equal to omega square into a square minus x2 square. So simply let's say this is equation number 1, equation number 2. When you will subtract these two equations, what you will be getting is v1 square minus v2 square is equal to omega square into x2 square minus x1 square over here. So this will simply give you omega, which is nothing but root under v1 square minus v2 square upon x2 square minus x1 square. So obviously the time period would be nothing but 2 pi upon omega over here. Okay, let's take one more question. It says the time taken by a particle performing SHM to pass from A to B, where its velocities are same, is 2 seconds. So we have already learned that for two different positions we can have the same velocity. So it is talking about the same situation, and after 2 seconds it returns to b. What will be time period? So let's try to solve this question using the reference circle only. So say this is the reference circle, and we are looking at two positions when we are having same velocities. Okay, so let's say like one of the position would be this and the another position would be this. Okay, so they are at same distance from the mean position. So here velocity would be in this direction, here velocity would be in this direction. So same velocities in fact we are having at these two position, and it is given that in order to reach from here to here, let's say A to B, it takes how much time? That is simply 2 seconds. And it again says like from B to again it reaches B. So you should realize the next position it is talking about is nothing but this position. Okay, so on its projection will again reach B. So rather this position is A and this position is B. So and this is B, and let's say this position here is B dash on the reference circle. Okay, so again it is given that from B to B dash it is taking 2 second time. So you should realize from A to B it is taking 2 second time, and from B to B dash it is taking 2 second time. So same time interval, and it is moving with constant angular velocity. So that means same angular displacement. So this angle here will be this angle. Okay, and you should realize the sum of these two angles is nothing but you can say pi. So this phase difference, simply this delta theta, you should realize is nothing but pi by 2, or you can say from here to here it is pi simply, and from here to here it is covering pi radians. Okay, so omega you can simply find it out is nothing but delta theta upon delta t over here. So delta theta you should realize from here to here is only pi by 2, and from here to here it is taking 2 second time. So that would be omega would be nothing but pi by 4. So time period here would be nothing but 2 pi upon omega. So 2 pi upon pi by 4. So that will be giving you 8 seconds simply. Okay, so this is regarding the velocity. Now let's also look at the acceleration as function of x. So looking at acceleration as function of x, you should realize that a can simply be written as minus omega square x. So when you will be plotting this graph a versus x, so let's say this is a and this is x, the graph will be having will be like a straight line. Okay, between these two extreme, x is equal to minus a and x is equal to plus a over here. Okay, so you should realize the graph would be something like this. Okay, and here according to this relationship over here, the most important thing to realize is acceleration is always opposite of displacement. Okay, from mean position, that is directed towards the mean position always. Okay, so with these information, a is equal to minus omega square x, and v is equal to plus minus omega root under a square minus a x square. Okay, let's develop one important table over here. Okay, and that table basically, if we know x, okay, we will be able to tell what would be v, okay, and what would be acceleration, because these relationship we know, no, that is plus minus omega root under a square minus x square, and this is nothing but minus omega square x. Okay, so if we have got this column, we can develop another two columns. So for example, again my pen is not working, so let me do some stuff over here. Okay. Okay, so let's say x is equal to 0 we are taking. Okay, so x is equal to 0, If we substitute it in this equation, we will be getting plus minus omega a, and acceleration here will be 0. If x is equal to a by 2 we take, or plus minus a by 2, we will be getting plus minus root 3 by 2 a omega, and this term here would be nothing but minus plus, rather you must say, that would be omega square a by 2. Okay, and the next term we can take like x is equal to plus minus a by root 2. So the corresponding velocity here would be nothing but plus minus 1 by root 2 into a omega. Okay, and this here would be, let's close this file. I think this will help us saving some. Okay, so, and the acceleration here would be nothing but minus plus omega square a by root 2. And the next entry let's have is plus minus root 3 by 2a, and that would be plus minus 1 by 2 into a omega, and this would be minus plus omega square a into root 3 by 2. And let's have x is equal to plus minus a, then the velocity here will become 0, and acceleration will again be maximum, that would be minus omega square a. So this table is very, very important, which enables you to find out, like if the position is given, you will be immediately able to tell what would be its velocity and what would be its acceleration. And now let's look into the energetics of the situation. Okay, energetics of SHM. So first let's talk about kinetic energy. Okay, so we have been representing like V as a omega cos omega t, and as a function of x it was represented plus minus omega root under a square minus x square. So knowing the velocity, we will be very easily able to tell what would be kinetic energy, because that would be half mv square. So as a function of time, you can represent it as half m omega square a square into cos square omega t, and as a function of x you will be able to represent it as m omega square into a square minus x square. So this is the kinetic energy as function of time and position. Okay, and the second is, let's talk about potential energy also of the particle executing SHM. Okay, so you should realize the change in potential energy du is defined as nothing but minus f dx, and f can be written as minus ma dx. So a as a function of x we know, because the variable here is x. Okay, so this will simply give us m omega square x dx. So du is equal to m omega square x dx, and if you integrated both side with proper limits over here, let's say 0 to x, and this let's say at origin we are assigning the potential energy to be 0, so 0 to u, that will simply be giving you u is equal to half m omega square x square. So please understand, when we are writing this, okay, x we are taking it as displacement from the mean position, because we have assigned 0 coordinate to the mean position, and the reference we have taken at the mean position, the potential energy we have taken it to be equal to 0. So this is the potential energy as function of x, and potential energy as function of time also you can write, because x as function of time we already know. So that would be nothing but half m omega square a square sine square omega t. And you should notice that when we will be calculating the total mechanical energy of the particle executing SHM, so that would be nothing but E is equal to K plus U, and adding these two terms, for example this term and this term over here, or this term or this term over here, that will be simply giving you half m omega square a square. And let's term it as some E naught, and you can say that is nothing but a constant because it is not varying either with respect to position or with respect to time, you should realize. So when we will be plotting energy time graph or position energy position graph, let's see how will it look. Okay, so let's draw energy time graph first. Okay, so you should realize first of all, so let's say this is time. So kinetic energy was represented as half m omega square a square cos square omega t. So this is also a sinusoidal function because see, half m omega square a square and cos square omega t you can always write. So that would be nothing but 1 plus cos 2 omega t upon 2 over here. So you can see that this is also a sinusoidally varying function, and here the frequency would be nothing but 2 omega, where omega was the frequency of SHM. Okay, and this is how the kinetic energy graph will look like. Let's say this would be the reference. Let's say that is E naught, that is half m omega square a square. This graph will look something like this. Okay, and please notice the time. This would be t is equal to 0. This would be nothing but pi by 2 omega. This would be nothing but pi by omega over here. This would be nothing but 3 pi by 2 omega, and this would be nothing but pi 2 pi by omega. So this is the kinetic k versus t graph. Okay, and similarly, so this is basically the potential energy graph. Okay, and because that is sine function, kinetic energy graph will look something like this. So if this is basically, we are having this. So this is kinetic energy graph. Okay, so you can see that u versus x graph is u versus t graph is this, and k versus t graph is this, but there's some here, that is the e versus time graph. Okay, so that would be a constant over here, and you should realize like it is repeating its pattern at this regular interval over here and this regular interval, and this interval you can see is nothing but pi by omega only. Okay, so you can understand that the frequency, since the frequency is getting doubled, its time period will be getting halved over here. Okay, and also you can find out, like for example, average kinetic energy for a period, or average potential energy for a period as well. So that would be nothing but you can say half m omega square a square. So you can take either the sine square omega t for potential energy and cos square omega t for potential energy, and you can understand like the average of this function is nothing but half. So this will turn out to be 1 by 4 m omega square a square, or simply you can say that would be nothing but E naught by 2. Okay, so average of kinetic energy or potential energy for the complete oscillation would be this much over here. So now let's also very quickly look into energy displacement graph. Okay, so energy displacement graph, we had equation for kinetic energy as half m omega square a square minus x square, and the potential energy graph was nothing but half m omega square x square. So when we will be plotting these graphs over here, okay, between the two extremes, x is equal to plus a and x is equal to minus a over here, the potential energy graph will look something like this. This is u, and the kinetic energy graph will look something like this. That would be inverted parabola, and this graph here would be nothing but the total energy graph. E is equal to E naught. Okay, so that you should understand. And the another important thing regarding this, like the average of potential energy and the average of kinetic energy, for example, when the particle moves from here to here, you should realize. Okay, so let's try to find that out. So average potential energy from 0 to A. So the function defining that would be nothing but u dx. Okay, upon say integral of dx, and we are averaging from 0 to A, 0 to A, and u we know that is nothing but half m omega square x square into dx, and that is from 0 to A, and that divided by A will simply give you 1 by 6 m omega square A square, which would be nothing but E naught by 3. You realize. And similarly, if you take the average of kinetic energy from 0 to A, okay, you can do k dx from 0 to A upon dx, that is from 0 to A, and k we know is nothing but half m omega square into A square minus x square dx, and that is from 0 to A upon A, and you will be getting over here is 2 E naught by 3. Okay, so you have to understand the average of potential energy from 0 to A is only E naught by 3, and average kinetic energy for the same path, that is 2 E naught by 3. So you should realize the meaning of this thing is simply that the for the longer part of the journey, okay, the kinetic energy was more. Okay, the kinetic energy was more for longer part of the journey. And here our time is up now, so I will be stopping here. In the next class we will be dealing with dynamics of SHM. Okay, and